So, good morning, all the participants. Now, we are going to start our next session, and here today our speaker is Professor Madhusudan Singh from DTU Delhi. Now, I'll give a short introduction to sir. He is a professor in the Department of Electrical Engineering, DTU Delhi. He received BSc degree in Electrical Engineering from Faculty of Technology, Dayalbagh Educational Institute, Dayalbagh, Agra, and the MA degree from University of Allahabad and PhD degree from Faculty of Technology, University of Delhi in year 2006. He joined Department of Electrical Engineering, Delhi College of Engineering, that is now Delhi Technological University, New Delhi, and where he is now professor in the Department of Electrical Engineering. Dr. Singh is a member of Institution of Engineers and of the Institution of Electronics and Telecommunication Engineering. He is a life member of Indian Society of Technical Education, New Delhi. He is also a member of Institution of Engineering Technology. His research interests are modeling and analysis of electrical machines, voltage control aspect of self-excited induction generator, power electronics and drives. Sir, I welcome you on behalf of Electrical Engineering Department, NIT Patna and Atal Academy of AICTE for delivering the today's session on power electronics converter for the renewable energy application. So thank you, sir, for accepting our invitation. We are very happy to have you here today.
Okay, thank you, Dr. Ambarisha, for inviting me for this interaction. It's a great opportunity for all of us to meet together, even not physically, but in a mode I hope we never thought earlier, online mode. Hopefully, most of you are doing your activity online. One way I find it's easy for all of us because this transportation issue and all now no problem. We can talk to each other, we can interact with each other sitting anywhere in the world. So thank you, Ambarisha, once again, and if you allow me, I can go ahead.
Yes, sir. Yes.
I hope my voice, video, etc. clear.
Yes, sir. Yes, sir.
Well, so as I saw the topic of this FDP is electrical and computer engineering, and keeping that thing in mind, I planned this interaction, considering that we have a very wide range of participants, mainly a few newcomers in this area of power electronics, few established researcher, also few obviously faculty members. So I planned my this talk accordingly, and I hope that you will enjoy that, being the fact that these more complex technical things I try to skip, considering the diverse nature of gathering. So let me present the content of this talk. So are you able to see this slide?
Yes, sir. Now it's available.
So I hope this slide is visible to you all.
Yes.
The topic for the today discussion is trends in power electronic devices, converter technology and applications. As I said, I have made it very general, starting with a few initial slides on the motivation on power electronics, especially for beginners. And then I will come to a few converter topology, which are especially useful for renewable energy applications. I am Professor Madhusudan, as Ambarisha already conveyed you. I come from Delhi Technological University. Hopefully, it is a state university of government of the city of Delhi, uh, and I am from Electrical Engineering Department. Uh, I will try to focus mainly on these points for the today talk. I set few slides on the motivations related to power electronics. I mean, what is power electronics? A very common questions which comes in our mind. And nowadays, since in electrical engineering, this word is very popular, most of the people wish to work, especially for the research and all. Uh, Especially the people who works in power electronics, for them, it's obvious question is why this power electronics is becoming important day by day. Something, as I said, it's a hybrid topic, electrical computer. Simulation is a very powerful tool in the modern world. And you know that any engineering system nowadays we think of, first we do simulation. And for simulation, I hope you all know the modeling is an integral and essential component. So that also I will talk you a little, and then we'll switch over to converter, and then the switches, especially power electronic switches, and finally few applications of power electronics related to renewable energy. Right? Hope I am going well. Well, so let me tell you what exactly we mean by power electronics. Power electronics is a technology associated with efficient solid state conversion, control, and conditioning of electrical power. So for power electronics, we refer 3C. 3C means conversion, control, and conditioning. The conversion, we mean conversion of one form of electrical power to another form. Maybe you have a AC power, you want a DC power, fixed DC power, or variable DC power. So that's the job of this power electronics. While doing this conversion, it may be a controlled conversion, it may be uncontrolled conversion, and many a times you need to improve the quality of power supply as well. That is what we mean here, conditioning. So you'll see that whether it is a task of converting energy from one form to another, controlling flow of power, or conditioning of electrical power, these all basically is a scope of power electronics, right? Now, as I said, P is basically an interface between you have a source and you have load this side. So the P is a interface between source and load, and it has mostly two words, as you have seen. There are two words, power and electronics. So when we say power, power means power converters, which do the job of conversion, one form of power available at source to another form of power which is demanded by this load. And to achieve this task, we have electronics. So this second word. So this electronics basically includes a set of sensors, intelligent devices, and other electronic components which altogether produces control signals which operate this converter to produce what is demanded by the load. So many a times you see that we have a very wide range of loads. They have very wide range of requirements in terms of voltage, current, frequency, and generally our source is of a fixed voltage, frequency, and nature. And to match these two, what is the role of PE? So this is what we mean usually the two words, but it's not only converter and alone which is able to achieve this task. When we talk a PE system or electronic systems, apart from controller, you have a drives, you have sensor, you have filters, and so many other elements when you talk about a PE systems. So you see that a PE system include all these controller, sensor, passive filters, which includes inductor, capacitors, and so many variety of things, right? Now, another question comes in the mind is that why PE has become so important, especially the higher efficiency. You know, higher efficiency is one of the key reasons to go for power electronic system. Now, how do we achieve high frequency in PE system? You can see in PE system, you have power capacitors, you have inductors, and you have switches. Now these switches are used only uh, in a in a on mode or in a off mode, not in a linear range. So you might have seen that a transistor, if you talk, you can operate in three different region of operation. You call it a cutoff mode, active mode, and saturation mode. Saturation we call on state, and cutoff mode we call off state. The linear amplification property it offers when it operates in active region. So you'll see that a transistor, if used as a switch, power electronics, every power device we use as a switch, and that's the region that if it is a switch, it is a switch mode. This transistor is always used in a switch mode. And if switch mode means if the voltage across the device is high at that time, say VCE if high, the current through the device is very low or almost negligible. So the power loss is almost negligible. Similarly, when device is in on state, the voltage is low, but the current is high. Again, the power loss is less. So switching action is the main reason to achieve a high efficiency. Linear range of operation, this is we don't do in case of power electronics. Now, let me tell you why power electronics has become so important over 5-6 decades. Right. Hopefully, those who work in the area of power electronics might be knowing that this is a technology which is started during 1957-58 with the development of a device called thyristor at that time. Right. And after 60, and if you see today to 2020, it's a hardly 60 year. It's just hardly 60-year technology. But if you see the development during 60 years, enormous development. Perhaps this is the one area of electrical engineering which has seen such a wide range of development over a very short period. In the technology, 50, 60-year-old, 50, 60-year period is not a wide period. So you'll see that 50, 60-year-old, what we wear in power electronics, if you see today, it is all different. Right? I mean, nowadays we rarely talk about thyristor-based systems. It's all what you talk about, either a MOSFET-based system or IGBT-based system. And again, I will talk again, a few emerging devices which have very bright future. What the power electronics people see. So let me tell you why power electronics has become so important. Now, it's not that before the development of the PE, that is before 56 or 1956 or 58, there were no way to control power. There were way to control power, but you see, you might be knowing the static control. Many of you, especially beginners or the student, might, while doing the experiment in the laboratory, you might have noticed we run DC motor, a variable speed using rheostats. Either you put a rheostat in armature or field and you change the speed. But you all know that what you do is you simply dump you have a fixed DC voltage and you dump a voltage, some of that voltage across these rheostats. I mean, you dump the power in a rheostat and it's a continuous energy loss. This is not at all a efficient arrangement, and this is why if you do the power control through electronic switching, this is many more times efficient than rheostatic control. Energy saving in another region, you'll see that when you do the control through switching action, the switching action is very efficient and therefore you save a lot of energy. And you all know that if you save energy, it is as good as reduce the generation. So as much we save, that much we need not to generate. And if you don't generate that much, you don't need to spend fuel for those generation, especially thermal power plant and all, need not to consume more coal and hence less environmental. So you will see all these three things related together. You save energy, you reduce the energy generation, and you are able to maintain a good environmental, ecological conditions. That's a major issue nowadays. So you'll see that in a recent study, in US, they said that 80% of air pollution mainly caused by their thermal power plants. So you can understand that generating using electricity, is always enjoying for everybody. But you'll see that how dangerous it is while generating, especially to the environment and all, and hence the human life. So this is another important issue that if we do the efficient conversion, we save a lot of energy. We need not to generate that much, and finally you can save the environment. Industrial process automations, nowadays you see most of the industries, modern industries are automated. Whether you go to Maruti or any chemical or fertilizer or any industry, you see most of the processes are automated. And the automation means, suppose there is a motion control, it is all through motor, and the motor is supposed to run at a fixed speed, fixed torque. So all those are achieved using only power electronics. And once you do automation, the major benefit you get is higher productivity and product quality. So this indirectly you can say power electronics enhance the productivity and product quality. Now you also had roughly 65% of generated energy is consumed by electrical drives. Hope you might be knowing the induction motor consume almost 60% of the energy generated over the world. So you can assume that this is a machine which is consuming 60% of energy all over the world. And if you adopt any efficient means to control such machines, there is a huge scope of energy saving. So such machines usually used to drive if it in industry, mostly for fans and all, blower, fan, and so many things. And you'll see that the efficient control of such machines is only possible nowadays if you go for power electronic based drives, what we call it AC drives. Similarly, if you see around 30% of energy is consumed by lighting systems. And I hope you could all have noticed that even in our generation we saw these variety of lamps, your conventional lamp, what you call incandescent lamp, fluorescent CFL lamps, and most call LEDs. Now what you notice in these bulbs and lighting devices is that this what you call normal long range bulb has a very small lumens per watt, right? Whereas if you CFL, you see it gives 63 lumens per watt, right? But if you see LED, this gives 73. So if you see the LED systems, they are 4 to 5 times more efficient than your conventional incandescent lamp, or even CFL is 2 to 3 times 3 to 4 times more efficient than this. This is a comparison table, and you'll see that these all applications, whether you call CFL based system or LED system, example of our electronics applications, right? You all know that this EV technology has yet to come in our country. But if you see in the two-wheeler and three-wheeler segment, almost 95% EVs are, and even the research in three-wheeler, four-wheeler, and even the buses and high capacity vehicles, the EV are yet to come, in fact. But you'll see that if these EVs all are powered through power electronics, and one of the reason to go for EV is, you all know that environmental pollution, obviously one reason. Another reason is high rising cost of petroleum products. Petroleum products are costing day by day, and again the cost also international market rising. So that's the reason to think for alternate means of transport. And you see the EV will all be powered through power electronics. You'll have a battery, you'll have a motor, but in between you need an interface for controlling motor through power electronics. So this is just a few applications. Now as on date, if I say what is exactly power electronics, it's very difficult to segregate. Power electronics is a technology which requires knowledge of electrical machines. If P is used to control machines, and obviously you need to know the devices, what we call power semiconductor devices. This is the most important component of power electronics, and you will see that whatever the development that took place in case of power electronics, it is all because of the development which happened in PSD. And the development which happened in PSD is all because of the development which happened in solid state electronics. So you'll see that the solid state electronics led to development in PSD, and then with development of new devices, we have come up to variety of converters, and those converters are used for many applications. So the knowledge of all these are integral part of our electronics. Apart from that, you know that converter control requires a lot of control algorithms, so knowledge of control theory. And to implement these control algorithms, you need intelligent devices, like you need microcontroller, you need DSP, you need FPGA, and so on. So you'll see that these devices used to implement these algorithms which controls these converters, and to have a interface between this intelligent device and power converters, you need certain drivers which are all analog electronics. So these all knowledge together, is important when you go for making power electronic systems, right? So a PE engineer, if he is one who have a good knowledge of all these area, right? All these area of electrical engineering. Let me tell you a few applications. As I said, nowadays it's very difficult to imagine life without power electronics. You think of any sector, right? Whether it's the industrial or commercial sector, you have power electronics, all the motors. This is when I say AC, DC drive means motion control. Motion control. So you all see that wherever you need a motion control, you have drives. Like in industry, you need furnace for heating purpose, right? Starters, soft starters for induction motors. So I hope you all know induction motor. Earlier we had a conventional starter, start delta starter, using especially contactors and timers. And especially if it is a very high rating machine, say if it is a 500 or 1000 kilowatt induction machine, the size of this starter, etc., very bulky. Nowadays, if you see, this is all done through your drives. So drives do the job of a starter also. And if you see the machine and has a on its top a small box, and that box is nothing but AC drive. What is inside that AC drive? Basically, a three-phase inverter, a rectifier, and a three-phase inverter, and some electronic controls based on microcontroller. So you'll see that such machines now, if you see any modern induction motors for industrial processes, they all come with a small box on the top of machine, and such machines we can call the smart machines. Smart machines means you don't need to have any device further for either protection purpose or starting purpose for these motors. UPS, SMPS, these are all commercial device. Everybody knows. We use in our houses. We know in our commercial activities. SMPS, UPS for driving your desktop computers or very any other emergency services where you need 24-hour supply. So, and not only that, if you see PE has good role in HVDC, the technology now based on totally power electronics, flexible AC transmission. I hope you all know flexible AC transmission, active power conditioning. Right, these are the few applications I cite in power system. Transportation, I hope, as I already said, EV has coming in big way in our country, and the government of India has set a target that by 2030, right, even 2024, almost 25% vehicle will be EV, right? And you can understand that if this big way, if it is coming, it requires a lot of technology development, lot of manpower training in this area. Non-conventional energy sources, this is what I will be talking little more in detail, right? Especially nowadays, if you think of exploiting power from any non-conventional energy, renewable energy, say solar PV or wind energy conversion system, it is all possible with the help of PE only. Domestic application, as I already said, you have charger, inverters, balance,
Sir, your
right?
PPT is not moving. It is only on the experiment variable speed air conditioner and that slide.
Oh, it is not fine. Is it okay now?
No, sir. No, sir.
Are we,
I think you need to share it again. I think slide.
so I will stop and again.
Yes, sir. Yes, sir.
Yora? I hope you are able to see this slide now.
No, sir. It's not coming now.
Sure. No, what I can do it. Stop sharing and then coming here. Uh, in this your meeting, I can go in open share mode. Is it?
No, sir. There is a up arrow. Just by clicking to that, you can share. Up arrow just in the side of mic on the screen.
हाँ इस आपको
Sir, are you getting the voice?
अभी फिर से शेयर करें अमरीश?
Yes, sir. Yes, sir.
अच्छा, ठीक है. सो मैंने आपको क्लियर किया एंड देन देयर इज ऑप्शन स्क्रीन शेयर. इसको क्लिक करें.
हाँ सर.
ठीक है. And then screen has come and then I can select and share.
Yes, sir.
अभी देखा कुछ?
Yes, sir. Now it is coming. Yes, sir. Yes, sir.
Okay. Okay. Hope you all are comfortable with this initial few slides on application and all.
It is power electronics spectrum.
Yes, yes.
Yes, sir. Yes,
So this is just for your information that PE has a very wide spectrum, and it covers now from milliwatt applications to megawatt, gigawatt, right? And I just collected few applications in different power range. If you see, less than 10 watt applications, you have flashes, strobes, laser, all these requires power electronic circuits. Satellite application up to 100 watts, right? Computer power supply, what you call SMPS, blender, in the range of 100 watt to 1 kilowatt, and so on. If you see, the now electric vehicles are coming almost in a very wide range. Your e-rickshaw, what you see, just less than 1 kilowatt, right? Few are just 850 watt and few are 1.2 kilowatts. But if you go in a four-wheeler segment or if buses, there goes in 100 of kilowatts. So these electric vehicles mostly covers this range. Buses more than 100 kilowatt, right? So 10 kilowatt to 100 kilowatt four-wheeler light vehicles, what we call car and all. There are few electric loaders also. They comes in this power range. So and if you go to megawatt applications, there are many megawatt applications, especially energy storage systems, magnetic energy storage system and all. Power plants using all power electronics, and you all know their capacity goes in megawatt for regulating the voltage, frequency. Alternators have solid state control, right? So all these, so we can say that P in fact has a very wide range, starting from few watt, milliwatt, going to gigawatt. This is what I said. What is a simulation? This word often we all come across, and most of when you do a project or research, you mostly talk about simulation. The initial focus happens to be on simulation, right? What exactly we mean by simulation? Simulation is a way of creating a physical scenario of the process or systems without actually developing them in real time, right? In real time. So this is what you do when you simulate a power electronics converter. We don't actually develop it, but in some software, we model them, right? Those model could be a MATLAB model, or it could be a PSCAD model, ETAP model, PSIM. So these are few popular software, and I hope you all might be aware. These are the softwares which we use mostly for simulation of power electronic system. LT Spice nowadays mostly used for modeling of PSDs, power semiconductor devices, especially if you want to model them with their characteristics and all. We use mostly LT Spice, and somebody was telling recently that LTP Spice models can also be linked with MATLAB model. So your overall system could be in MATLAB. Devices could be modeled through LT Spice, so that you get almost the real-time characteristics of devices in your actual systems. So this is all about the software, and now let us talk more about little power semiconductor devices. As I said, are the basic building block for now power electronic systems. PSD, in the word of late Professor A.K. Chattopadhyay. I hope many of you might be aware. Professor Chattopadhyay is no more, but he was one of the founding figure in our country in the area of power electronics. He used to say, PSD are the heart and soul of modern power electronic systems, right? One of the beautiful thing about the PSDs are they are very small in size, but they are very powerful. I will show a picture of few devices. You see that a 1000 volt, 1000 ampere device you can just put on your palm. A very small device, but you can see that they have enormous voltage and current handling capability. So that all makes overall P systems is smaller in size, weight, and cost, and that is what is the benefit of going power electronic systems, right? So how much time, Amrish, you have given me officially? I mean, by what time I have to stop it?
Sir, it can go up to 115.
115, right? So I hope we have still good time. So I will talk some more about this power devices, and then we'll come to power converter. Now let us me tell you that whenever we use a power device, power electronic device, whether it is a thyristor or a transistor or a device which comes under the category of uh, MOSFET and IGBT and all. What is the ideal expectation as a user? As a user, we have certain ideal expectation, but we never meet those expectations in real practice. Uh, that every device must have very large voltage blocking capability when it is in off state, right? So if it is in off state, the current through device almost negligible, must be leakage current, but the voltage across the device could be good, maybe order of 1000 or kilovolt. It should be able to carry very high current. So the current density is important. So in a small size, very high current capability, that's another feature what we expect mostly in the devices. Once the device conduct almost a very low resistance and hence low voltage drop, and the most important thing is that we should able to switch the device from one state to other state very frequently. This transition from one state to other state, whether you call on to off or off to on, must happen in few nanosecond, right? So that way we expect a very high switching frequency, uh, and keeping those all requirements in single device was always a dream, right? Was always a dream for P engineers. We try to improve one requirement, we sacrifice in terms of other. But nowadays, you'll see the recently in last one decade, we have seen the potential of wide gap devices. These wide, most of the conventional power devices which you might be knowing or which we use mostly in our laboratory, they are all silicon based device, right? And that's why silicon is cheaper in fact, and that's why we are able to afford those devices. But recently you have seen that there are some semiconductor compounds, wideband device are basically using semiconductor compounds, and these semiconductor compounds are these silicon carbide and gallium nitride. So GaN devices, now the people call the GaN devices, they are coming up with very good features. I will talk you later, but you'll see that in coming days, maybe after next 10 years or so, these all silicon devices market will be almost covered by these devices, especially the GaN devices. And GaN devices nowadays, if you see the manufacturers application notes, they cite a lot of scope in EV applications and all. So these are the characteristics of your device. I hope you all might be knowing in your. These are all standards just for your review. A ideal diode you expect that once in on state should carry full current, but at almost zero voltage. One in off state should block negative voltage but zero current. Similarly, a SCR is a device which always conducts current from anode to cathode, always forward current on state, but it can block voltage either positive or negative. That's the beauty of SCR, that it can block positive voltage, negative voltage, and it remains off, right? A diode cannot block positive voltage, it can block only negative voltage. BJT, you see here, can block positive voltage, but it has no negative voltage blocking capability like the MOSFET, right? These are the switch which you can't use in for reverse voltage blocking, like in rectification and all these you cannot use. GTO has also a device like SCR, so it has a blocking voltage positive as well as negative, but the negative voltage blocking capability is relatively lower than positive. IGBT is basically a hybrid of the BJT and MOSFET. I will talk you later. I hope you might be knowing IGBT stand for insulated gate bipolar transistor. So a device of transistor family which covers the feature of BJT and the MOSFETs. The good feature of BJT, good feature of MOSFETs. Has a characteristics, if you see, almost like your SCRs, right? But again, here the voltage blocking in negative region is slightly lower than positive, and the IGBT has different structure. Maybe might have come across called punch through, non-punch through. Accordingly, the reverse voltage blocking capability differs. Now, if these all what I showed you in these slides were the good aspect of power electronics, right? Why the power electronics has become important. Mostly I cited the good things about power electronics. Now let me tell you what are the few challenges associated with power electronics. Whenever you make PE systems, there are three major issues. One is the losses that you see is almost covered nowadays by using the more efficient devices, less switching losses. But harmonic is another issue. As I said, PE systems are interface between source and load. The load has a different requirement. Source has a fixed nature of its terminal behavior. So when you use power electronic system, it's basically do switching action on your normal supply. So your supply voltage in fact are switched, right? And when you switch through solid state switches, what we call power electronics devices, PSD, there are always creation of harmonics. In fact, PSDs are also non-linear units. So whenever in a system you introduce any non-linear element, the non-linear characteristics of the element is basically responsible for generation of harmonics. I hope we might be knowing this fact. What is source of harmonics? Non-linearity is the source of harmonics. So non-linearity. You all know that whether if I take ideally a diode, this is also a non-linear, and discontinuity in voltage and current. Or you have a transistors which has characteristics like this. That also you have seen. These all are non-linear devices. So whenever we use such elements in making a system, they all are the good reason to create harmonics. Now the issue is that whenever you do switching action, there is a generation of harmonics, and those harmonics affects your systems, that the power supplies, right? We will see the adverse effect of power electronic system on our utilities or the grid. Adverse effect of PE systems on utilities and their remedies, it comes under an area called power quality. So Ambarisha, did you have any talk on these power quality issues in your earlier slots? Or I hope this is today is your second day, or
Second day.
Today is second day. So you had a talk on power quality with the earlier experts?
Yes, sir. No, in the morning, we have some discussion with the Professor Sailen Jain, some power quality improvements, active
Achha,
power filter and all. We have just discussed the things.
achha. So I have something on that also. I will that quickly skip that.
But no, sir, he has discussed about the simulation only,
Achha,
simulation of the filters.
achha, achha. So I have
So,
also few simulation result. I will show you. But what I told you that in power electronics we have mainly three major issues, right? One is the losses, other is harmonic, and third is EMI. So any PI systems, PE system we develop nowadays, it has to be looked into EMI issue also, electromagnetic interference, what you call. So there must be in the shielding and all to avoid that. And at the same time, the harmonics which are created through switching actions must also be compensated, and this is what I hope Professor Salanjan could have thought of, that could have told you that there are different devices, there are different type of compensators which can eliminate not only harmonics but like other things also. That all comes under area what is called PQ now. Power quality is another area, in fact a sub area of power electronics. EMI is another sub area, right? So those who works in the EMI protection of devices and systems, I think that's another interesting area of power electronics. Now let us losses. When I say mostly the conduction losses, switching losses in the devices, you all know that every device conducts, and it goes from off state to on state. It has finite time, and during that the voltage current may both be available, so that during transition period the voltage current both may be available, and that may create loss. But once it goes either in on state fully or off state fully, then obviously out of voltage and current, one parameter obviously gets lower, and the losses becomes losses. Harmonics, as I said, the chopping current voltage generates harmonics. Whenever you have, say, you have a sine voltage like this, you call supply voltage, and you uh, rectify it. So you put a diode rectifier, you get a V naught. So the moment you put a diode rectifier on this kind of supply, so you have a AC supply Vs, and if you put this AC supply to a diode rectifier, could be a bridge rectifier or any other configuration, and this side if you put some inductive load and all, you will see that this side is a DC voltage, but this current is no more sine, right? So what I am telling you is that when you get this uh, unidirectional voltage from a bidirectional voltage through switching action, uh, in those cases, the switches which are in this rectifier, they create some harmonics. So what I am trying to tell you is that the harmonics are the outcome of switching action in the P converters, right? These harmonics injects high frequency current into your input supply voltage. So that is the issue. So you see that such harmonics, if goes into supply, the supply performance deteriorate. The voltage profile of the supply may distort. So you all know that you have AC source. It is AC source which basically developed, or AC source we generate with the help of generators, right? Or we create through with the help of generators. Now every AC source has certain impedance, right? Source impedance, and when you draw a current here, source current, which is not a sine current, if it is a non-sine current, then there is a voltage drop in this ZS, that is ZSIS, this is a distorted voltage, right? Because the current is not signed. So this voltage drop creates this terminal voltage further distorted. So what I'm trying to tell you is, when the currents are injected into the source profile, the source voltage get distorted, right? That's the major problem. How do we do those correction and all? I will take up. This is just a history. I can skip, the whole thing is started with the development of uh, uh, you know the SCR, in fact 1957. But prior to that, if you see the greatest evolution what we have seen in the history of electrical engineering is the development of transistor, 1948, in the Bell Laboratory by what the joint effort of three scientists might be knowing: Braden, the Shockley, the Breton, and broadly, I think. So these three people together worked on development of solid state transistor at that time, silicon transistors, 1948. And I think thereafter the same laboratory, Bell Laboratory, was able to give the concept of your silicon control rectifier in 57, which was later on commercialized by GE Electric, right? So GE Electric commercialized this product, though the 56 the SCR was. So now the PE start, this is the start of history of PE, right? PE started from 56, and you see nowadays, 2020, we talk, this is all a wide and wide band gap based devices era, in fact. So these are some basics. I can skip it, in fact, the characteristics of many devices and all, right? Hopefully you might have done it some stage. Now what is interesting, the device which has become most interesting nowadays, especially in power application, is IGBT, insulated gate bipolar transistor. In fact, this is a device, as I said, was developed in 1983 Jayant Balika, hopefully you might be knowing. And you see that this device has seen a very wide scope now, and people call it a device of choice for industry, right? It is a device of choice for industry, a choice for industry, right? Most of the high power devices, whether you call inverters or power supplies and so many applications you talk about, if in a high power range, especially more than 100 kilowatt, you'll see they mostly use the IGBT. Was developed by an Indian, in fact, Jayant Baliga, but not in India, in US, right? Jayant Baliga is still professor, I hope, in some university of US. You can see the biography. He's an IIT Madras graduate, right? The device was developed in 1983. The beauty of the device is that it covers the interesting feature of BJT and interesting feature of MOSFET. That's why we call it a hybrid device. But it's also a member of transistor family. So you might be knowing that BJT has a very low conduction drop. VCE, SAT is very low. This just 0.3 for silicon devices, right? And for a MOSFET, you all know that its switching frequency very high. So the reason is that its gate is almost isolated, does not draw any current. So no gate uh, current gives you a good scope for frequent turn on and turn off. So the high switching frequency of MOSFET, low conduction of BJT was an effort to combine in IGBT, and in 1982 that was achieved. Now this device, as I said, has a more or less uh, you'll see that it has a voltage drop slightly higher than BJT, but its switching frequency is slightly lower than MOSFET, right? It means it covers the good feature of BJT and good feature of MOSFET. That's the good thing about BJT, IGBT, and you'll see that even for high power application, the drop across device is not much high, as it happens in case of MOSFET, right? MOSFET has another limitation. When it conducts, the voltage drop across MOSFET was very high, right? Because of this RDS on happens to be of the order of milliohm. Well, so this device, what I said, has good scope, in fact, and now recently, 1957, ABB also worked on a similar device called IGCT, integrated gate commutative timer. I mean, this is a device where the gating circuit was packed with the device in the same the gate is integrated within the device, right? But this device is yet to commercialized because of its technological limitation and all is still not come up, but was launched long back, in fact, almost 20 years. I think that the detail of these devices I will scope. This is just for your uh, few slides of Professor Ekuchettopadhyay. You see where he has shown the how these devices look like a GTO, which is a gate turn-off thyristor, right? 6 kV, 6 kilo ampere. You can put in on your hand, but you can imagine that such a small device can handle very large power. Similarly, this is a high voltage thyristor, SCR, what we used to say, comes in a power pack. This is called power pack configuration, in fact, of thyristors, how it looks like. So these are a few interesting thing about these devices, and let me come to the other aspect of this power electronics, that is power converters, right? Uh, Power converters, you can say it basically a matrix of switches, right? Any converter is basically a combination of power electronic devices. So a set of PSD together connected in certain manner create a converter. The converter has different role. If the input is DC, you want a variable DC, it could be a DC to DC converter, right? Input is AC, you want DC, we call it rectifier. You have input DC, you get AC output. This is what is the job of inverters. And AC to AC converter, they are also called nowadays matrix converters. And earlier we had similar device we used to call cyclo converter, AC voltage regulator, and all. Right now, this is just the same thing. Now let me talk about little on this issue what Ambarisha was telling, that power quality has become an important issue in power electronics nowadays, right? If you have because the power electronic systems are coming in big way, so if there are a huge number of P systems connected to your grid or your power supply, and if all start injecting some harmonics to your supply, then the harmonics content in the supply becomes very significant. Now the issue is that how you can eliminate those harmonics, and this in spite of reducing your P systems, with the existing P systems, how you can improve the power quality, right? I mean, how you can ensure that the harmonics and all are not harmonics, etc., are not a problem to utility people. So broadly, when I say what is one language, when we say power quality, we broadly refer to the delivery of a sufficiently high grade electricity, right? When I say high grade electricity, it is just like, you have a raw water and you have a distilled water, right? So you all know that most of the people drink, raw water, but there are few people who demands for distilled water also. Distilled water, is as good as your good power quality power supply, right? Now, when I say uh, power quality in electric supply, it is basically maintaining a sinusoidal voltage, right, at the load end, right, and also the sinusoidal at load and bus voltage, right? Maybe you have different type of load, but suppose the load is an AC load, we don't want that your load should distort this power supply. So if this is your source VS, whatever the load you connect here, you never want that the profile of VS should get a distorted sinusoidal. You remain want that VS should be a sine voltage Vm sine omega t. Now, so that's the issue. So maintaining a sinusoidal voltage at this terminal, again of a fixed amplitude, fixed frequency, is basically what is maintaining power quality, right? So you will see that even you change the loads here, the load could be a rectifier, load could be a drive here or a motor. They should not alter the profile of the voltage of the source in terms of the magnitude, the frequency, and all, right? That is what broadly we refer. Now, as I said, that so most of industrial automation is happening with the help of power electronics, and that's why the productivity and is all we all expect a higher and higher productivity, and that's why we go for automation. So with a higher productivity, if you want to ensure power quality of product as well, you need to maintain the power quality in the systems, right? Because you all know that if it is a mm, if it is a company producing, say, cotton mills, right? The clothes are manufactured. You all know clothes are made on a rolls. The rolls are driven by motors at fixed speed. If there is a fluctuation in the supply, the roll speed will vary. You see that that rolling process all will get disturbed. Quality of cloth will all get distorted. What I'm trying to tell you is that it's not only higher productivity, but product quality is important. Quality you can maintain only if the quality of power supply you maintain. Power quality is not only a technical problem, it has become now a financial problem, right? Because if you are not able to maintain the quality of your product, you lose in terms of the product cost, right? If you are not able to produce good quality product, nobody will purchase, and all know everybody expects distilled electricity. Now the issue is who maintains the power quality, right? What are these problems associated with power quality? You can understand, especially in distribution system, I mean the power you and we use mainly from distribution network. They have very common problem of under voltage, sometimes over voltage, right? Sometimes there are notching, right? Harmonics, that is the distortion. So flicker, voltage flicker, these all are the power quality. DC offset has become now another problem. In your AC, there are some DC components. So how to voltage unbalance, another major problem is you have a three-phase, three-phase, four-wire system. We are unable to ensure equal loading on phases, and that's why you see the voltage in one phase is different, other phase is different, and that leads to symmetrical components and all issues. So unbalanced voltage is another major issue that is. Now, these are few standards. I hope many of you might be aware. IEEE 519, most of our electronics people use to know how much harmonics labels are prescribed at distribution end. 5% THD at the in the distribution system, specified by IEEE 519. So this is basically an harmonic standard 519, but recently you could have seen there is a standard 1547. This is a standard mainly on how much the what are the deviations which are expected when you connect renewable sources to the grid. So if you connect renewable energy sources, how much voltage variation, how much DC offset, how much harmonic injection at the point of common coupling you can allow. That is what comes in 1547, IEEE 1547. So those who works in area of renewable energy system, you can tell. I mean, you should refer, in fact, these standards, especially that how much DC offset, how much harmonic, how much voltage fluctuation and all at the point of common coupling your system is going to affect, right? Well, this is what is power conditioning. I hope I might have seen this arrangement that whenever you have AC source, you feed a
Sir, your voice is not coming properly. Sir?
sends the current, that is compensator current, in such a way that the sum of this and this remains sine, right? So to make this square a sine, whatever is needed, that is so this the compensator current is nothing but the the source current minus your load current, right? So source phase A current or phase, if you are talking phase C, then this compensator current is the source phase C current minus load phase C current. So whatever is the difference that is being compensated, nothing but a set of switches you see here, S1, S3, S5, and basically a power electron. So in other words, I can say that whatever the danger you pose on the supply due to power electronics, that danger is also removed by the power electronics. So any bad effect it creates, that bad effect is also compensated by the power electronics. That's the beautiful thing about power electronics. So any harmonics which are supposed to come in the supply are being supplied by these compensators now, and therefore there are no harmonics in the supply. So this how it is achieved, this is a very elementary and broad concept. How it is achieved, I can show you in the next few slides. This is a system, three-phase, three-wire system, right? You have AC source, right? And you have the load here, linear and non-linear loads. So you have some RLC load, you can assume maybe some motor load, or maybe non-linear load means some rectifiers load also here. So because of that, this side current is no more sine, obviously. So if this current, load current are distorted, and still you want that the source current should remain sine, you need a compensator. So these are the compensator. Compensators are basically, you can say, in other words, they are active filters also called, or a popular term used for compensator is called statcom, right? If it is a distribution system, we use a statcom to improve power quality. It is called d-statcom. Statcom for distribution, right? So it's basically a three-phase VSC, right? Three-phase voltage source converter. So there is a three-phase switches here. In fact, 6 switches inside this box, and the control of these 6 switches are achieved through by providing switching pulses based on what kind of compensation you want to ensure here. Whether you want to ensure here only reactive power compensation or a harmonic compensation, or load balancing. So that we will see what kind of compensation this can provide. Same compensator can do multiple tasks, right? Can do the job of harmonic compensation, can supply reactive power here, can maintain good power factor at the load. So for that, you need to plan your controllers, in fact, and the controller, what you see in the initial slides, is basically this part is your controller part, right? This is your power converter or power electronics converter. This is your normal AC source, and this is load. So apart from the source and load, what you need to have a PE system here and a controller, right? And nowadays in most of the research and all, the controller we use DSpace 1104 or nowadays. This is also micro lab box, I hope, right? So how to control this inverter is a major task, in fact, and I hope to control these inverters. I think in your morning lecture this might have been discussed. Now there are different control theories. One of the popular and conventional theory is synchronous reference frame theory, SRF theory, right? Right, and this SRF theory is based on two transformation. One is called Clark transformation, Park transformation. Now this is Clark, right, transformation. This is Park transformation, right? So how a Clark transformation used to convert three-phase load current into a two-phase current in alpha beta reference frame. And again, this alpha beta current, if you convert into a stationary reference frame called LDLQ frame, this is what is called synchronous reference frame theory. So this mathematics, what we used to call a transformation uh, matrices, can be used to implement this SRF theory, and I hope those who are interested might be using these standard relations for these conversions, right? There is again, if you have a two-phase, you can convert into three-phase, right? This is called reverse Clark. So a three-phase was converted to two-phase. It's called forward Clark, and a two-phase converted to three-phase is called reverse Clark. Similarly, a reverse Park also. So these two transformations, if you use and you control those VSC, what I saw here, right? This VSC, if we convert, I mean, the switching pulses you generate using this concept of SRF theory, you will see that these are few standard result. This is a supply voltage, three-phase supply voltage. You see sinusoidal voltage. This is source current, right? You see here the source current remains high, right? In spite of your load current is square, right? So this load current, if it is square, you see this is the compensator currents. And this is the current which is supplied by VSC. So if you suppose this is the blue color is the load current, phase A load current, you see the blue color of compensator current, this If you add these two, it will make the sign. It means what is missing in a square to make it sine, that is all provided by this compensator. So you'll see that this compensator is basically able to create a necessary component which makes the source current sine. So it's not only compensating, it making the current source current sine, but you see the source current is also balanced. And though you see load current, you see the phase C is open at this moment and this remain open till t equal to 0.4. So t equal to 0.3 to 0.4, you see the phase C is not there, but you see from the source phase C is current is there, and hence the source is still balanced. So what I am trying to tell you is that this SRF theory, if used to control your VSC, the VSC is able to ensure a sine profile of load source current. It also maintains the source current balanced, right? And it also eliminates the harmonic from the source current. So the multiple tasks, in fact, achieved by this. Now, this is all about the THD, in the voltage and current. This is source voltage as only fundamental. So here it is assumed that source voltage is pure sine. Now only the source current is to be maintained sine in even the load current. So you see the load current is square very high THD, 27%, right? A different harmonious component like this. But with the help of compensator, you see the source current has only fundamental. It has no harmonics. It means the harmonic is being all supplied by the compensators. Harmonics are not coming from the source. So you see the THD in source current very low, 2%, 2.2%, where the load has very high harmonics requirement. That all harmonic requirement met by your compensator. It is not coming from the source. So this is a very conventional theory, I hope, for power quality. Another is power balance theory. I hope this also based on the power relation. In fact, if you know the terminal voltage of your load, right, and uh, the terminal voltage of your load, since the load current, three-phase load current, right, and three-phase supply voltage, so if you see that the phase A voltage multiplied by phase A current, phase B voltage multiplied by phase B current, and so on. This is the three-phase power, right? This three-phase is instantaneous power. And if you pass through a low-pass filter, you will get the average power, the real power, right? And similarly, you know that you have a VSC on the DC side, you have a capacitor, and we need to maintain the DC voltage. So we measure the actual DC voltage of the DC link, VDC. We compare it with a reference DC, how much we want to maintain, and the difference is passed through PI controller. That much real power, either you have to supply to charge the capacitor, and this real power and this real power is the net real power, which must come to the source. So accordingly, the source reference current is created, right? So how much source current actually, how source power is demanded, accordingly, the in phase component of source current should come from the source, and accordingly, you have actual source current that is sensed, right? This is what is the source current which we need to actually create, called reference current. So these reference currents and the actual currents are compared in a hysteresis current controller, and they used to produce gating signals. So this is a theory, you see, where again the gating signals are derived based on the power calculations, right? The real power calculation of the load, how much real power the load is demanding, in addition to the real power demand to meet the switching losses, as well as maintain the DC link voltage. So both together decide the net real power power, and to meet that much real power, how much current, real power component of the source current must be there. That is what is called reference. So these two compare, right? So this is just a control theory PVT called power balance theory, and these see the simulation results here. And you have seen that the PVT, the THD of source current is further reduced. So you'll see that which theory you use, which type of load there is there, and that all decide that how much effectively you will able to eliminate harmonics. So if you see here the THD, if you are able to reduce, earlier it was simply 2.2, here 1.42. So it means this is more effective here, right? PVT is more effective for that same load. So this is just to tell you that how these theories are applied. And similarly, there is a reactive, instantaneous reactive power theory, IRPT. Those who works in area of power quality might be knowing all this, right? And these also requires a reverse and forward Clark transformation, right? But here what we try to see that the two component of the power, the reactive power and real power, are calculated by using the transformation on the three-phase current and three-phase voltages. So you apply Clark transformation in the source voltage, three-phase voltage, as well as three-phase load current. And this voltage and this current will decide how much is the reactive power demand of the load, how much real power demand of the load. If you pass this through a low pass filter, you get their average values, and further the DC link voltage you can add, and finally you can create a source current, reference source current will compare with actual current, and that is again will use to produce the gating signal for VSC, three-phase VSC. The result are there, and you see here the THD in fact is not uh, reduced significantly, but it is still high compared to other two. So you'll see that for same load and same operating conditions, which control algorithm will be effective, it's all depends on the nature of load and all, right? So now let me tell you a few applications of power electronics in PV, right? Solar PV, I hope you all know, is coming in big way in our country. Reason being that it's a green the sun energy available in abundance. The only problem is there are certain uncertainty, depending on your climatic conditions. Sometimes the sun is available, some is not available. But you see in our country, I think there is a majority of time we had a good sun. So how to exploit the sun energy to get electricity is basically what is the purpose of this discussion. So we use again power converters for solar PV applications, right? Solar PV applications, and what exactly is the PE? In fact, this is, I think, the model of solar is called single diode model. Single diode model of a diode and a solar cell. How to represent a solar cell with this model and these resistances. And I hope these circuits with there is appropriate equation and are already now modeled in MATLAB. Those who do study, they are using this ready-made model of PV. So you will have a PV, and then obviously the output is DC, and then this DC voltage need to be converted into an AC voltage, right? So, and before that, what we need to do is that this DC voltage need to be raised to a higher level called through boost converters. So usually in our PV systems, you'll see this is the standard characteristics of PV. One is called current voltage characteristics, other is called power voltage characteristics. So you see that both are a function of the radiation level, what you call irradiance level, that is standard is 1000 watt per meter square, but there is a variation in irradiance level from 700 to 1000, and you'll see that accordingly you see the radiance is low, the current produced is less. And similarly, the power also, if you see the power voltage curve, this is the blue, and again for low radiations, the power also comes. So you see that the peak power is continuously changing depending on the radiation level. And if you want to extract maximum power, you have to use some maximum power point tracking techniques. One of the common technique people use is perturbed and observed method. Like, every time, so we try to see the power slope, whether we are this side or this side, right? And that way you can detect this maximum power point, and you can operate your uh, boost converter so that in such a way that you are able to extract maximum power. So you'll see that in most of the PV systems, the boost converters are used to these boost converters are used to maintain the MPPT, right? To realize the MPPT algorithms in boost converters. And so the DC voltage, you see, in normal now grid systems, grid tied PV systems, we have number of panels which you can connect them in series and parallel to get an appropriate DC link voltage. And then boost converter, mostly the duty cycle of boost converter, we don't use to boost this voltage. Rather, this boost converter is used to implement your MPPT algorithms, right? So that even the radiation is changing, we track the power from maximum power point. And so you have a DC PV, and then you have boost converter, and then this boost converter is connected to the DC link of this voltage source inverter. This is the DC link. And this boost converter, this VSC is now controlled in such a way that you are able to inject power into the grid. So this is the general scheme. So here no battery, because this is a grid tied solar PV. So the grid, if available, the power is injected to the grid. This is just a standard rating of this system for which some study is made by one of our research scholar. These are few control algorithms, and you see here, this is without PV, and this is with PV, right? This is with PV, this is without PV. So you'll see that if there is no PV system, whatever is the load 450 watt, that is coming from the source, right? And you see here, with a PV systems, you see what is the demand of load. Only 250 coming from source, the remaining is coming from your PV systems, right? So this compensator power or PV power is this. So one of the theory is used as RF theory, in fact, to control this VSC and relations here. One can use all these theory. I think we have already tried all these, and a few publications are already there on this notch filter, standard second order, generalized integrator, and all. So these, I hope those who might be working in this area may be aware of these type of systems. Now these are few standard results. You see the source voltage, the load current, and we have created all kind of changes in load, say unbalancing the load. Still we are able to balance the source current. This is source voltage and this source current and load current, right? And the DC link voltage is also regulated. So these very small variations and all. So this is just to, and few applications of wind. So if you have time, I can tell you something on winds. I think the time is over, is it, Amrish?
Yes, sir.
So I think it is all. I have a very wide range of slides.
Yes, sir. Yes.
Our time is not possible to cover all, but those who are interested, these are few wind applications. I will just skip these slides for your visual observations. Few slides, the offshore wind farm. These are vertical and horizontal turbines, right? And the most popular configuration used to extract wind power is this DFIG systems, where you see the power is supplied to the grid from the stator as well as the rotor. So we control this rotor current, and that regulates this power supplied real and reactive power from the source. So here you need a power converter which is a very small size, just 30% of the power rating of this generator, because this has to just handle the slip power. Slip is 3%, so accordingly power rating is low. That's the major benefit of this configuration, and this is a configuration which is more popular nowadays. So I think this is all about my today presentation. These are few applications of EV. I hope you all know electric vehicles, how there are converters in the electric vehicles. We have a battery pack, DC to AC converter, which drives the motor, and motor is connected to the wheel. Through this is the powertrain and a gearbox and all. Sometimes it is used with gear, sometimes without gear. So if it is a without gear, this simply motor is driving the powertrain, and you have a battery, and there is a charger for the battery. So you have a battery pack. This part is the charger. This is the motor controller, and there are few DC to DC converters for some auxiliary supplies, because in electric vehicle you need power supply for various electronic and other components. So accordingly there are some DC converters. So this is all about EV has also a good application of power electronics. I think this is all from my side in this short interval, and uh, if you have any query, I had few more that I can skip because your time is over. So this is all from my side, Amrish, in this short interval, and if there are any queries, I will happy to
So
address.
participants, now if you have any query, you can ask it regarding the presentation and whatever the contents are as delivered.
Your most of the participants are the teachers, or they are the students?
Maximum they are teachers,
They,
sir. But
also
some of them they are the MTech or PhD students.
there are few PhD MTech students, obviously.
Yes.
So those advanced work, I think, especially on Power Quality and all, might
Yes.
be referred to those people who are working in those area. And for teachers, I think my initial slides could have been some informations, right?
Hello.
Yes, yes.
Good afternoon, sir. I'm from Mumbai, VGTI College. I
Yes.
was working in this field that you have used this SRF method and PBT method. Can
Yes.
this incremental conductance IC method can be used in this system or not?
Well, IR method and this P and O both are used for MPPT in solar. But
Yes.
there are certain issue with IR method, especially at low radiation level. There are oscillations in tracking of the maximum power point. So
Okay.
I think there are a few research paper you can refer where they have done a comparative study of these methods for
Yeah.
solar application, and the cases of oscillations are cited, especially in low radiation conditions.
Yeah. And second important thing, sir, if unloading condition happens, then how we can control in this? And if the order of the system, suppose second order, third order system is there, then how we will do this?
What do you mean by control? I mean
Sir,
this. No.
uh, hello.
Yes, yes. You are working for some research work, or I mean, I just want to know what reference you are asking this question.
Sir, what type of controller we can use in this IC incremental conductance method?
No, controllers, in fact, are nowadays very wide range. If you see, those who are in research, they use a very advanced controller like a fuzzy controller and others, learning-based controllers. But you see, mostly for our study, we have used a conventional PI controller. Conventional PI controller. Conventional PI controllers quite effective in maintaining DC link and all, even in varying solar conditions. Yes, if there is any other query, then I can reply. Otherwise, if it's all okay, then we can wind up from this.
Yes, sir, we can find up now. I think if there will be any query, we will let you know if
Yes.
required. So
So,
thank you very much, sir, for being here and delivering this level of content to this program and benefit to this all the participants. So thank you, sir.
thank
We
you.
can
Thank you.
have the chance in future also. Thank you.
Sir, please share this your slide to me because I
Yes,
need
that I
to.
will
Thank
provide at the end.
Okay. Thank you, sir.
you all for
Okay, thank you, sir.